Picture this for a second. You're floating through a totally dark cosmic background. All around you, the vacuum of deep space is just filled with these glowing atoms and swirling molecular clouds. Imagine brilliant blue energy waves shooting through the void, lighting up invisible, tumbling molecules in this huge quantum landscape. Welcome to this explainer. I'm Dr. Chem, and today we're going on a cosmic zoom. We're going to discover our very origins by tracking how tiny, unseen molecules tumble through the deep interstellar dark. You know, the McGuire Research Group actually frames our mission perfectly. They say that the study of our cosmic origins, literally everything from the Big Bang to the molecular building blocks that hitchhike to Earth on meteorites, relies entirely on observing molecules outside our solar system. I mean, these vast molecular clouds out there, they're star factories. They're these unique, almost magical laboratories where incredibly rich, exotic chemistry is constantly churning out the essential building blocks of life. In fact, over 200 distinct molecular species have been found so far in these star-forming regions. Crazy, right? So let's dive right in and figure out exactly how we pull these secrets out of the darkness. Okay, so to really understand this, we need to take a look deep inside TMC1. This is a cold, dark molecular cloud hanging out in the constellation of Taurus. Now, if you look at TMC1 with a regular optical telescope, it just looks like a whole lot of nothing, an empty void. But chemically speaking, it is a bustling, chaotic laboratory. The exotic chemistry happening in this freezing environment, we're talking literally just above absolute zero here, is actively forging the precursors to life. But, well, if it's completely dark and absolutely freezing cold out there, that brings us to our million-dollar question. How do we actually see what is totally invisible to the eye? Think about it. How can we possibly detect and map these distant molecular networks when we literally cannot see them, and they're drifting thousands of light years away? It's not like we can just fly out there and scoop up a sample of TMC1 in a jar, right? We have to rely on a totally different kind of light and a very, very specific kind of molecular dance. And the answer to that mystery is rotational spectroscopy. So as a molecule tumbles end over end in the vacuum of space, it emits a highly specific electromagnetic fingerprint. We map this via long, low-frequency waves in the microwave region, specifically wavelengths ranging from 3 million to 300 million nanometers. To wrap your head around that, instead of the tiny, rapid ripples of visible light, picture these massive, invisible, rolling waves washing over our radio telescopes here on Earth. The signal we capture is basically this giant, messy chorus of all the overlapping spectra from all the molecules tumbling in that spot. So to pick out a single molecule in space, we first have to recreate it, tumble it, and measure its exact microwave fingerprint right here in our terrestrial labs. But hold on, there's a catch. Not every molecule gets to play in this cosmic broadcast. There are some hard and fast rules to this quantum rotation game. First up, the sample has to be in a gaseous state at ridiculously low pressures, around 0.01 millimeters of mercury. Second, and this is absolutely crucial, the molecule must possess a permanent electric dipole moment. It needs a positive end and a negative end. And third, as it rotates, that dipole has to appear to fluctuate to interact with the microwave radiation. So what does this mean? It means perfectly symmetrical homonuclear molecules, like the oxygen or hydrogen we have here on Earth, are entirely inactive. They're totally invisible to this multi-million-dollar space sniffing technique. To really get why this dipole thing matters, let's consider hydrogen chloride, or HCl. The math behind the magic here is actually quite simple. P equals Q times D. P is our dipole moment, Q is the charge, and D is the distance between those charges. Because the heavier chlorine atom hogs the electrons, pulling them away from the hydrogen atom, you get this permanent separation of charge. So as this molecule tumbles around, its glowing dipole vector rotates too. It essentially acts just like a tiny spinning antenna that can dynamically absorb or emit a microwave photon. Now, when a water molecule gracefully rotates, its shape is what dictates everything. You see, microwave spectroscopy depends fundamentally on a molecule's principal moments of inertia, which are mapped across 3 distinct axes, IA, IB, and IC. Depending on how the mass is distributed around these axes, molecules get classified into different groups. If all 3 moments are equal, you've got a spherical top. 2 equal? That's a symmetric top. But for water, none of the moments are equal. It is an asymmetric top. And that asymmetry gives us a wonderfully complex, highly unique rotational fingerprint that we can actually track across the entire galaxy. Let's zoom in on the quantum mechanics for a second. Picture these transparent quantum energy ladders rising right out of a dark, sci-fi-looking scientific landscape. You see, a rotating molecule can't just spin at any random continuous speed. That's not how the quantum world works. Its energy levels are strictly quantized. We label these levels with the integer j, so j equals 0, 1, 2, 3, and so on up the ladder. When our molecule absorbs a microwave photon of the exact right frequency, boom, it instantly jumps up a rung on this glowing ladder. But here is the thing. You can't just jump to any rung you want. The quantum selection rule dictates that the change in j, delta j, must be exactly plus or minus 1. No skipping steps. A step up means absorption. A step down means emission. And actually, here's a fun reality check. Real molecules, they aren't perfectly rigid little things. As they spin faster and faster at those higher j levels, the chemical bonds actually stretch out due to centrifugal distortion. Think about how you feel pulled outward when you're spinning really fast on a playground merry-go-round. It's exactly like that. This tiny stretching slightly reduces the rotational constant, so the rungs on our glowing quantum ladder actually get a tiny bit closer together the higher up you climb. Okay, so how do we actually measure all this in a lab? Well, we rely on two main highly advanced instruments. The first is the chirped pulse FT-MW spectrometer. Think of this as casting a massive wide net. It pulses a huge 10,000 megahertz bandwidth, rapidly profiling entire spectra at once. But it does have slightly lower sensitivity. The second tool is the cavity-enhanced FT-MW. This one is like a sniper rifle. It has a very narrow 1 megahertz bandwidth, but it is unbelievably sensitive and precise. In modern labs, we basically combine the best of both worlds. We use the wide net of the chirped pulse to spot the cosmic fingerprints, and then the sniper rifle of the cavity instrument to measure them with the extreme precision we need to match the telescope data. But what happens when we're trying to find molecules we don't even know exist yet? Well, that requires some seriously brilliant detective work. It's a screening method. First, we set a chemical reaction in motion using precursor molecules we already know are hanging out in TMC1. Second, we analyze the known reaction products. Third, and this is the genius part, we mathematically strip away all those known spectral lines from our data. What's left over? A mysterious list of unknown signals that correspond to brand new chemistry. Finally, we use advanced techniques like AMDR to classify those remaining unknown signals and figure out exactly what we're looking at.
Right, so how do we connect the dots on those unknown signals? That is where automated microwave double resonance, or AMDOR, saves the day. Imagine this exhaustive, automated routine where we pump high-energy light at one specific spectral frequency to intentionally deplete another. If altering one frequency reliably messes with the other, we've definitively proven that both spectral lines share an energy level, and that means they have to originate from the exact same unknown molecule. It's kind of like 2D NMR, if you're familiar with that. It gives us the molecule's rotational constants, basically its size and shape, without us even knowing what the molecule actually is yet.
Once we have those constants locked in, the real magic happens. Microwave spectroscopy isn't just about figuring out what a molecule is, it's uniquely powerful for determining exquisite gas phase molecular structures. By analyzing tiny shifts in the data when we substitute different isotopes into the molecule, we can pinpoint the exact locations of individual atoms to fractions of an angstrom. To put that into perspective, that is less than a billionth of a meter. We can literally map the 3D geometry of these building blocks with stunning precision, finding their exact bond lengths and atomic locations as if we were holding them right in the palm of our hand. So let's pull back for a moment. As we zoom out from these tiny rotating molecules, revealing this vast cosmic network of interconnected atoms glowing across the universe, we're left with a pretty profound thought. We've built the tools, from massive radio telescopes scanning the heavens to those highly sensitive microwave spectrometers in our labs. We're actively matching the fingerprints of creation. But as we continue to map these cosmic networks, you really have to wonder, what other life-essential molecules are still out there, hiding in the dark, just waiting to be discovered? I'm Dr. Chem. Thank you so much for joining me on this explainer, and remember to keep looking up.